Right, I guess I'm live. Hey everyone, I'm Ashish. Welcome to the AI Bootcamp. So now I'll be explaining to you vgg16 transfer learning, and let's go. So it's as easy as clicking the launch lab button, the magical button, open code server. Yeah, all right. So first of all, I'm opening this cats versus dog vgg16 full file, and you may need to install TensorFlow data sets. As I believe there are some packages I intentionally left uninstalled so that you also know like how to install them, and how you would install them would be first of all, activate the required kernel, which is we will be using TensorFlow environment. So to activate it, we will paste this command source of activate, and then we will be using this command pip install TensorFlow datasets. It will install the TensorFlow datasets for you. I have already installed it, I guess, so I don't need to install it. Then I will go inside the deep learning folder by saying change the directory into 14-day bootcamp, and I'm pressing tab to autocomplete. Then I'm saying go inside the folder 5. I'm pressing again tab to autocomplete. Let me show you again what I'm doing. I'm saying change the directory, and let's put it inside double quotes right now. 14-day bootcamp and 5 machine learning, because I'm putting the double quotes in, so there are no backslashes. That backslashes, yeah, those were weird backslashes. So let's see. Let's understand the code first of all, like what we are trying to do over here. Some ports are opened, so I will close them, and also I will search for NVIDIA SMI just to ensure if we have all the memory allocated to us available to us, which it is. Clear the screen and let's get started. So first of all, some basic imports like OS, JSON, TensorFlow as TF, TensorFlow datasets as TFTS. This is its own API, which is different from TensorFlow, but it is very tightly integrated with the TensorFlow, as you will see. Some imports like from TensorFlow import Keras, layers, vgg16. What vgg16 is basically, it's a pre-trained model, a model which was pre-trained. It's a model or architecture. vgg16 would be an architecture. So this is how things look like with vgg16, and it works very absolutely good. So it's like if you don't want to train your own models, vg16 is there. Someone else has trained a model for you. Use that rather than training your own custom models. So convolution layer, and you can see like what the exact branching and pattern of the layers is. So 16 is because there are 16 layers over here. All right. So okay. And this pre-process input is for VG16, and what it really does is it uh, in simple words, it just takes your data and converts it into the way in the format VG16 as a model expects. That's it really. You don't have to understand the mathematics behind VG16 or pre-process input. Some lines which are supposed to help with OOM error. Supposed to. I don't know if that will or not. Configuration. So this data set that I will use, I will be having a lot of images in the data set. So one thing that I know or need for sure is consistent features. So 160 by 160, I need to have images size of, you can have any kind of custom size, but you need to make sure that every image that you're training your model with, all the images, every image that you have in the training set, all those images should be of same size. If they are not, just resize them using OpenCV or whatever tool. Batch size 16 means like in one epoch, how many instances should your model look at in one time? That's basically it. Autotune is used with TensorFlow datasets. Uh, I would say, what is it called? TensorFlow data. Autotune is used with TensorFlow datasets to increase some optimization. I don't know how it works. No, nor do you need to know how it works. So then I'm creating data directory, model directory, and plot directory, as you can see. Then I'm loading the dataset tfds.load, and it gives me this train ds and validation ds. So this isn't a NumPy array. This isn't a TensorFlow tensor either. It's some type of TensorFlow datasets kind of object. And you don't really need to understand at the moment like what this particular data type is, because it contains your data, but you cannot just simply visualize it because it's not images exactly. It's TensorFlow object that has been downloaded for you. And we will use data augmentation. Data augmentation means that if you have one image, you can create many images out of it. Like by if you have one image, flip it a little bit, flip it a little bit, rotate it, flip it, and basically what we are using is random flip of horizontal, which will be like this. If you have an image like this, flip it horizontally. Random rotation would be something like this. Random rotation of 10% angle. All right. Then random zoom of 10%. 10%. So that's how you take one image and create several images out of it. Then the pre-processing function goes, our own custom model will be using this pre-processing function. So tf.image.resize, what we are saying is tf.image, resize this particular image into this 160 by 160, then flatten. No, it's not like not flatten, but normalize. And then return image and labels. Yep, fair point. And then pre-process VGG is for, take a look. We are normalizing to 0, 1 in our custom model, but in VGG, we are using just the pre-process input, but we are also required to resize into 160 by 160. Then we will train some pipelines. So we will say that train DS, which is really a data object of TensorFlow datasets. So dot map this particular function with the help of no, I mean dot map the particular function, but use this functionality as well of auto-tune, which will supposedly help with faster training. As I've read somewhere, it's what it does is it does the pre-processing and training together, but I don't really know how it works. You don't need to know how it works either. So for our CNN pipeline, we have train DS, validation DS, dot map, their own pre-processes function. Then for then I'm saying shuffle. This is like a manual, very manual API. Then I'm saying like shuffle 1,000, uh, take 1,000 images, shuffle them up, create a batch, and then prefetch of autotune. Prefetch, I don't know what really it is. I found this kind of code in the API. Let me show you where. And TFDS prefetch. So you can read it over here if you want to, like how this is supposed to work. So this entire loading a dataset of TFDS goes something like this. You create a autotune, you load the dataset, you dot map the particular function and autotune. Then you shuffle buffer size, something it is. Then you give the batch size, then you prefetch with the autotune. And then the dataset is now ready for efficient model training. Let me zoom in a little bit. Yeah. So this is how you load your data sets using TFDS API. All right. So the same thing we will do with vgg16 pipeline. And now let's build our custom model. So we are saying keras dot sequential. First of all, use the data augmentation. Then use some layers of convolution max pool, convolution max pool, convolution max pool, and keep on increasing the neurons from 32, 64, 128. Basically, experiment with different numbers to see how things work. Initially, I'm taking 32 features. Then after another extraction, I'm saying like let's say 64 new features, then 128 new features. Then these are mathematical layers. Mathematical layers, I'm using dense of 128. Then I'm using dropout regularization of 50, which meaning that really in one iteration, turn off 50% of the neurons so that it is supposed to control overfitting. Then because we have cats versus dog classifier, so we have only two classes. So we can predict the two classes with just a sigmoid function. All right. Then we are building VGG pipeline. So VGG is like something that somebody has trained the model of VGG on the ImageNet dataset. This is the ImageNet dataset. Let me show you. ImageNet dataset, I believe, is of 1,000, or let's just open the images. ImageNet dataset, I believe, has 1,000 classes. It was trained on 1,000 classes, something like this. Yep. So I believe there were 1,000 classes in ImageNet datasets. So right now, what we are trying to do is predict into cat versus dog. So what we are trying to predict are just two classes. But ImageNet was trained when VGG was trained on internet on 1,000 classes. So we gotta remove the final layer, like final layer of prediction. So just like we have our final layer of sigmoid, we of like sigmoid and these flatten, dense, dropout, dense. We will use this almost same structure except the final. We will remove the final layer of vgg16, and we will introduce our own custom layers. And this is the functional API I told you that we will be using. So here it goes. I'm saying create a base model of VGG which has been pre-trained on ImageNet dataset, but don't include the mathematical layers. Those dense layers don't include. I will use my own dense layers because I have my own predictions to make. Input shape is 160, 163. Base model not trainable. Don't make the base model trainable at all. Then base model dot output is something like X. So you can create or save this as any kind of thing. Take the output of output of base model and pass it as a function inside global average pooling. It's like flatten only, but we are averaging out rather than just flattening out. What I would mean is, like if you have a 3D array, you flatten it out, it spreads over. If you have a 3D array, you take global average, then global average would mean that take average of RGB channels, RGB channels, and so on. Not really RGB channels, but in a nutshell, you're just taking average. So like let's say if you have a 3 by 3 matrix, 3 by 3 by 3 matrix. So 3 by 3 right here, 3 column, 3 row, and 3 depth matrix you have. Then if you flatten it out, it will be 3 multiplied by 3 multiplied by 3, which is 27. So 27 numbers will be there. But if you take global average pooling, what it will do is it will take the 3 rows, 3 columns, but what it will do is it will average along the depth. So the output would be after global average pooling, the output would be 3 by 3 only. So that's the difference between flatten and global average pooling. Take the average of the depth channels, which I believe in this case would be the color channels. So I'm taking the base model dot output as input for the next layer. Then I'm taking this layer as input for the next layer, which is dense. Then dropout. Then then uh, final layer is dense layer one activation sigmoid. We are putting our own prediction layer and calling it outputs. So we have an input and an output. So keras dot model input is our base model dot input. which is really nothing but the pre-processed data that we will be having, and outputs that we have created just right here. And this is the functional API. So return for me the model in the base model. Base model and model right here it is, and base model. I'm returning base model as well. Okay, okay, okay. I guess it will be important. Then I'm saying that let's train the models. So with this variable, basically I'm controlling that if the base model will be trained or not. So if you train the base model, the model would be huge and it will be slow to train. So that's why you need functionality to train the base model or not. So sometimes you would want in hyperparameter tuning section to train the base model as well. Sometimes you don't want it because the pre-trained features are really good. So model.compile, model.fit, and I'm saying if base model is not none, then fine tune it, unfreeze the last four layers, unfreeze it. And basically you can unfreeze the entire base model or whatever you would want. I'm just taking the last four layers right now. You could take any, you could just say for, just like you said in here, somewhere you said, somewhere we said na base model dot trainable equals false. We could definitely very well say that base model dot trainable equals true somewhere. Yep. But we are saying that let's keep only four layers trainable so that our model is trained faster, then compile, then dot fit, and then merge the histories. Like for I in history dot history I plus history. So what it will do is basically it will merge the histories of the models, then save the model and open the history and dump it as history.history jsdson.dump and return the history. Then I'm training the CNN model, build CNN, train model, and then I'm deleting it to say to clear some memory because VGG model is heavy. So VGG model over here, train model. What to train it with? All the parameters right here. VGG model is right here. Train VGG right here. So let me show you what these parameters were. So model, train data, validation data, name, whatever you name you would want to give it. Where am I using name parameter? Right here. I'm using the name parameter. Anyway, so after that, some plotting is there, and that's it really. So let's run this particular file. So I will say Python 3 uh, 5 cats versus dog full pie. Okay, so let's see the training happen in live. It will be a little slow to train. First of all, we are training the CNN model. First epoch is going on. It will take a lot of time. So meanwhile, you could just skip the video ahead. I'll sit and wait for it. Second epoch, and the validation accuracy is 62%. Okay, 71 it has reached in our custom model. Basically, I'm totally expecting my custom model to not perform that good as my VGG model, and I'm not expecting my VGG model to work good either because my VGG model was never trained properly. Really, if you wish, you could just you know train the entire you could train the entire pipeline like this. First of all, uh, make the VGG model, freeze the layers, don't train them, and then keep the dense layers over here. Train only the dense layers because dense layers computes the mathematical equations for you. Then make the entire pipeline trainable. Then train the whole model for 5 epochs. and then freeze these base model and then again train. So keep on doing this kind of thing until really you achieve what you the desired output. I mean, right now I'm training the VGG model. This is the base VGG model where I'm keeping base VGG model as non-trainable. So I'm training really three or four layers, which was like dense dropout and the sigmoid layer final. So I'm really training only three layers in this particular model, and the validation accuracy is already reaching 94. But it's very slow to train. You can see that our custom model was very fast to train because it was really a small model, and the VGG model is taking around 41 seconds. I know that watching this would be a little complicated, but if you follow along, write everything step by step, you would get more gist of how this thing is going, because we are not going into notebook mode right now. Because in the notebook mode, as I show you, you would be facing out of memory errors. That's why we are doing the script first approach right now. In Google Colab, but it's feasible to train your models on a notebook, but you in Google Colab at least you are not able to what should I say? You're not able to create applications like what we will be doing right now. In a while, I will show you how to make a Streamlit app out of it, so that if you upload a video, I mean, if you upload a photo into the system would be predicting if it's a cat or if it's a dog. Almost 50% done we are. After this, fine tuning will be there. I mean, take a look, yeah. How cool is this? Like we started off with nothing but zero knowledge of coding, and now we are training deep learning models using script-based API. I mean, script-based approach. Now we are fine tuning, so I am expecting the fine tuning to be even slower. Let's see how long it takes. Oh, it took almost the same time, 41 seconds for the non-trainable base model version and 42 seconds for the trainable. I see what's going on. It's because we are training, we've unfroze only last four layers, so not a big impact that made. In the meantime, let's discuss the that app, that Streamlit app that we will be making. in a while. It will take first of all the model path, image size, because once you train a model with this kind of size, you have to input this kind of size for the image for predictions as well. We will load the model, we will pre-process in the same way, like resize, convert it into array, and then pre-process the input np.expandums, create a basically data set out of it. That's what this would be. But if you were to ask me what expandums mean, that it would take the image of, let's say, 160 160 comma 3, and it will just introduce a new axis to it. So now the shape would become something like 1 160 163. So initially it was a 3D array, now it will be a 4D array. It's saying streamlit.title, dog versus cat classifier, streamlit.write, whatever you would want to write, streamlit.file uploader, choose an image and upload it, and basically some code, image.open. This is from the PIL library, I believe. Yep, from PIL, import image. So I'm saying image.open this uploaded file, dot convert it into RGB, and print the image. Use a button with a spinner, and there you go. It's really a short amount of code. Our model training is done. So let's now run this Streamlit app that we have over here. So to run this, you need to go down a little bit. And how to run a Streamlit app basically would be, Streamlit is installed inside the data science environment. So you go and activate the data science environment just like this. And to run the app, you would say streamlit run app.py server address blah 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 server port blah blah blah. Some basically ports. And if this port is not available, change the port. Like let's say right now I'm opening the app on 8501 port. If it is busy, if the port 8501 is for some reason busy, you just put in 8542. But we are using only once. I mean, we are opening the Streamlit app only once, so it should work. Now it's saying that your application is running on port 8501. So open it in the browser. I will open it. And here we go. We have the entire Streamlit lab app. Just drag and drop a file. So I will choose this image dog.jpg. So first of all, print the dog.jpg. Then we have a print predict button, spinner, analyzing images, and it's a dog with 100% certainty. And we will be making better apps with time. But for now, let's be content with this only. And with this, we are done with our deep learning section. Almost done, because we have not discussed the natural language processing, but we will discuss it maybe later on. So thank you for watching, guys. I can understand if the deep learning model, especially the deep learning model, was a little complicated, but try it on your own. It's all hands-on. Try it on your own, code it on your own, and you will be very well equipped with the task of doing deep learning. We will be making a lot of apps later on as well. Apps like this. Acha, we will discuss the app later. Chalo.